One of the main tasks in sustainable construction development is reducing the mass of buildings and structures. One way to solve this problem is to use lightweight and lightweight concrete on porous aggregates. Despite the constant increase in lightweight concrete structures, their share does not exceed 30% of reinforced concrete volume. The release of load-bearing structures from lightweight and lightweight concrete is primarily constrained by the absence or shortage of suitable and durable porous aggregates. Therefore, the production of artificial porous fillers from local raw materials significantly wastes from the mining and metallurgical industries, is of exact importance. Mining and processing plants of Ukraine annually store more than 130 million cubic meters of sludge. Only in the Kryvyi Rih iron ore basin, more than 2,000 hectares of agricultural land are occupied by dumps. Part of the enrichment waste, with a particle size of more than 0.14 millimeters, is used as sand and crushed stone. However, a significant amount of waste has a particle size of less than 0.14 millimeters, not currently used. Therefore, developing a technology for obtaining sustainable porous aggregates for concretes using finely dispersed waste from mining and processing plants and concretes based on them continues to be an urgent scientific, technical, and social task. The research aims to develop optimal compositions of new porous aggregates made from the waste of mining and processing plants and study these aggregates' properties. The selection of the optimal composition of raw materials for the porous filler included an analysis of the influence of the charge and additives design and their granulometric composition on the final product's quality. Dry mixtures contained crushed and not crushed sludge, grains with a size of 1.25, 0.14 millimeters. Not crushed sludge with the addition of crushed shale. Not crushed and crushed sludge with the addition of crushed shale. Crushed sludge and crushed shale. Dosing of the dry components of the charge carried out by weight. The content of crushed sludge and shale is taken as a percentage of the total dry ingredients. The rate of consumption of alkali silicate is taken from the total weight of the charge. The mixture was granulated in a disc granulator until granules with a diameter of 5-20 mm were formed. Liquid glass is fed into the pelletizer by means of a spray gun. The molding of the raw granules was carried out at different density values of alkali silicate, 1.30, 1.45 g/cm3, which provided the introduction of the required amount of its solid substance into the charge. This approach made it possible to reveal the pattern and nature of the influence of the consumption of alkali metal silicate on the porous filler's properties. Raw granules burning was carried out at 950, 1050, and 1150 degrees Celsius for 5, 10, 15, and 20 minutes. Further analysis of the results showed that firing longer than 10 minutes had no significant effect on the parameters investigated. The burnt granules testing results from a raw mixture with crushed sludge in its proportion shown in Fig. 1. The obtained results show that if alkali silicate and the amount of ground sludge in the charge increases, the average density of aggregate granules decreases. However, it is impossible to obtain an aggregate with an average density of less than 1.5 g/cm3 due to the resulting liquid phase's small amount. The amount of the liquid phase largely depends on the content of fine particles in the mixture. The amount of ground sludge did not exceed 20%, and the larger grains did not take an active part in creating the pyroclastic melt, they dissolved only partially. Adding a part of crushed shale to the slurry made it possible to obtain an aggregate with a lower average density than in the previous case. This dependence showed in Fig. 2. A decrease in filler granules average density with the same fraction of the crushed charge occurs due to an increase in the liquid phase amount. This is because liquid glass forms more melting eutectics with shale minerals and more intense gas evolution occurs. Studies have been carried out to study the content of crushed silt and shale for the aggregate average density. These studies' results are shown in Fig. 3 and show that aggregate granules average density decreases almost linearly, increasing alkali silicate consumption. However, with a 15% content of crushed sludge, shale, and alkali silicate consumption of more than 10%, an increase in aggregate granules average density is observed. A decrease explains this in the melt's viscosity and the process of compaction, rather than porization. The combined effect of the milled components on the aggregate granules average density is greater than that of each separately. Previous studies have shown that using a mixture containing unmilled sludge and shale results in low-strength granules with low porosity and high average density. Therefore, all further studies were carried out only on mixtures with ground components. The results showed in figures 4 and 5. Dependencies show that the most intensive decrease in average density occurs when there is up to 40% shale in the charge. A further increase in the shale amount reduces the average density slightly, but the granule strength sharply decreases, and the pores increase due to increased gas release. Intense and excessive release of gaseous products does not improve the porization process but causes the formation of large interconnected pores, passing into cavities and open pores. Since previous studies have established that the most suitable for obtaining a porous aggregate is a crude mixture consisting of crushed sludge, crushed shale, and water glass, these mixtures have been used to study the influence of technological factors on the properties of the porous aggregate. The research objective is to obtain mathematical models expressing the aggregate's average density and strength on the leading technological factors. The mathematical planning method, followed by mathematical and statistical processing of the results, was used to reduce the number of experiments. A three-factor experiment at 2 levels is planned in work. The variables are x1, the content of ground shale as % of the total mass of dry components, x2, consumption of liquid glass as % of the total mass of the charge, firing temperature degree. Since firing for more than 10 minutes did not significantly affect the parameters under study, firing the granules was 10 minutes and not taken as a variable. The levels and intervals of variation of the selected factors are shoved in the table. 1. After statistical analysis, the equations have the following form. When checking the suitability of the above equations by Fisher's criterion, they all became adequate. Analysis of equations 1 and 2 shows that within the limits of variation of the variables, the burning temperature and shale consumption has the most significant effect on the average density of the aggregate, and the effect of the burning temperature is 6 times greater than the consumption of shale. As the strength of the aggregate decreases, the burning temperature and the alkali silicate consumption increase. Figures 6, 7 shows a graphical interpretation of the obtained dependencies. Properties of porous waste aggregate. To obtain a complete characterization of a material and to identify its behavior in concrete, detailed studies of its properties, structure, and phase composition are required. The aggregates obtained both in a laboratory and in industrial conditions were subjected to research. The general view of the porous aggregate granules from the MBC wastes showed in figures 8. The samples of the obtained porous aggregates of dark brown color differ little from each other and have a large porous structure with cavities. The pores are generally round, 250-1000 microns in size. The surface of the aggregate is partially melted and differs from the inner layers in its lower porosity. The absence of a dense sintered crust on the new aggregate's surface is expected to increase adhesion to the cement stone, ultimately leading to an increase in concrete strength. The images were taken with a scanning electron microscope, SEM, to show a porous aggregate structure from MBC wastes, figures 9. There is a different size of porosity of the material. The pores have a smooth surface, and the surface of the chip partitions between the pores is glassy, homogeneous. The nature of pore formation is the peculiarity of the new aggregate structure. This process occurs due to the swelling of the pyroplastic melt. It results in an increase in the original volume due to the release of CO2 from the granules volume. An artificial porous aggregate from MBC wastes obtained in experimental industrial conditions were tested. The test results are presented in the table. 2. For experimental production of the aggregate, a mixture of mining waste and oil shale in the ratio of 4:1 by weight, liquid glass consumption of 8% of the mass of dry components and firing temperature of 1100 degrees Celsius for 15 minutes was used. As Table 2 shows, the tested aggregate meets the requirements of 9757 to 90 and belongs to the highest quality category. A cement stone's contact zone with a large porous aggregate, figures 10, has the form of a winding line exactly repeating the granule relief, providing a tight and robust contact. The micro-hardness measurement method was used to study the micro-strength properties of the contact zone. The results have shown that the micro-hardness of the aggregate, 9,000, 11,000 MPa, exceeds the micro-hardness of the cement stone in the contact zone, 4,000, 6,000 MPa, and the micro-hardness of the contact zone is higher than that one of the cement stone in the intergranular space, 1,500, 2,000 MPa. Conclusions. To obtain a porous filler, the most optimal is raw mixtures containing 20–40% shale and 6–10% liquid glass, fired at a temperature of 950–1150 degrees C. Mathematical models have been obtained that reflect the influence of technological factors on the volume, density, and strength of porous aggregates from the waste of mining and processing plants. The physical and mechanical properties of the obtained porous filler, characterized by high mechanical strength, have been determined. The filler meets the requirements of the standards and belongs to the highest quality category. The filler has a porous structure with a predominance of pores with 250–1000 m and is composed of mullite, corundum, albite, nepheline, and minerals of zeolite structure. In the contact layer between the aggregate and the cement stone, a chemical interaction occurs with the formation of hydrosilicates of the tobermorite type, contributing to strengthening and intergrowth with the cement stone.